sensing cap that was used in this particular application. And to be able to generate the PWM, the pulse width output, you pass the output of the upper branch and the lower branch to an XOR phase detector, able to come up with the difference in the pulse. So, in terms of what we done was, what the student done was use MATLAB to model each of the different blocks percentage. So this is a model of the circuit that was known using MATLAB. So we have the first block is the clock generator, the RC circuit, and then we also model the comparator, then followed by XOR. So to be able to measure the clock, so we look at the clock generator. So the main idea here is that the capacitance that can be detected by the circuit will be dependent on the target duty cycle and the target frequency of clock to be used in this circuit. So for the target application, the target capacitance range was from 1 picofarad to 20 picofarad. So that particular range a frequency of 12 kilohertz was determined. So we also looked at the different rise times and fall times in this particular model. And because of the differential operation, the delay, rise time, and fall time have minimal effect on the system output. So this is a sample of the clock generator. So the clock is shown below. So what you can see here is that the duty cycle is very, very big. So higher than 90%. And then those would be the outputs of the two comparators, and then the output as shown here. And then we also looked at the jitter, and what was seen was for uniform distribution of 1 picosecond to 100 milliseconds. Jitter didn't really have a significant effect on it. And in terms of the clock generator, what we see here is that in terms of the Csen, so the x-axis is the capacitance that you are sensing, the capacitance that the circuit is sensing, followed by the y-axis by the pulse within microseconds. And what is shown here is that the target range of from 1 to 20 picofarads was achieved, at least from a model's perspective. Now, in the implementation of the final circuit, there was a consideration on building a ring oscillator. But given the very, very low frequency of the clock, what was decided was to look at a different way of implementing inverters. In this case, we used a CMOS thyristors instead to be able to have a lower number of stages. So using the thyristors and 5 stages as a ring oscillator, we were able to produce the 12 kilohertz or close to 12 kilohertz clock frequency. And because of the lower number of transistors and blocks, the power consumption was minimized. So this is a clock generator using the CMOS thyristors as shown, where you have at least 5 stages implemented as a ring oscillator. And this is the generator layout for that particular block, for this particular block. So from the schematic, the target frequency was 11 kilohertz with a duty cycle of close to 97%, and a dynamic range of 1 picofarad to 20.5 picofarad. So what was achieved after the layout was a frequency of 10.61 kilohertz, a duty cycle of 94.5%, and a T-on versus available pulse width of around 19.43 microseconds. But it still allowed us to have a dynamic range of 1 picofarad to 21.5 picofarad. Okay, the next step is the RC sensing cap. So basically, the RC sensing cap uses or utilizes resistance and capacitance. So the idea here is that the rise times of your charging would be proportional to the resistance and capacitance of the 2 branches. So it controls the sensitivity because the higher, so for example here, Cmax determines the maximum capacitance that can be detected by the circuit, and it's proportional to your clock frequency and the duty cycle. But in terms of sensitivity, it's inverse, so higher Cmax means you have lower sensitivity. Now, in this particular implementation, what was determined was the resistance would be close to 1.75 megaohms. And then the capacitance for sensing was determined to be 0.55 picofarads for the reference. And then for the sensing part, it would be from 1 to 20 picofarads. So the main difference here is that, so we still have the resistance, but now in terms of the implementation, we also have a transistor that is parallel to the capacitance. Because right after you've charged the capacitance at the target threshold level, and the duty cycle, or when the clock begins to transition from high to low, the objective is to pull down the charges from the capacitance to be able to reset the circuit. And then lastly, we looked at your inverter-based comparator. So the inverter-based comparator will trigger the pulses that will be generated by the circuit. So in this case, in terms of a modeling, what you see here is you have your resistance and then the capacitance, followed by finite gain op-amp, which was modeled here as your comparator. And to be able to measure the non-ideal behavior of the amplifier, what was considered was to put an input resistance at the input of your amplifier. So in this sense, what you're seeing is that because of the input resistance, we see a difference in the pulse width that is generated. So the target is basically Rin should be much greater than the resistance of your RC circuit. So once the resistance and the Rin were determined, we've looked at the threshold voltage. And what you're seeing here is the variation of the dynamic range of the circuit versus the threshold voltage. And what was determined here is that for a threshold voltage of 0.9 volts, that's the value that will give us the target range, which is from 1 picofarad all the way to 20 picofarad. So because of this, target design for the threshold was around 0.9 volts. So the threshold value of 0.9 volts requires a V bias of around 1 volt as shown in the circuit. And unfortunately, because of this, only 60 millivolts of voltage is generated within the comparator circuit. So because of the 60 millivolts, it's the main effect now is that when you look at the pulse that is generated here, you see that the transition from high to low is weaker because of the sub-threshold operation of the transistors in the comparator. So what was done was to integrate or to put another inverter after the comparator to be able to balance out the rise times and fall times. And lastly, we're looking at, so this is the inverter buffer that was inserted. And this is the comparator threshold that was achieved. So it was around 897 millivolts. So finally, to be able to generate the output phase, we implemented an XOR circuit wherein the maximum allowed delay should have the same pulse width and should be able to charge to voltage high before the cap discharges. So in terms of delay, this is around 200 nanoseconds. So this is your standard XOR gate. So it is a full complementary implementation. So all available inputs are also provided, whether that's A bar, B, and B bar. And this is the XOR result, the gate results for your XOR, showing that your low to high transition is roughly 90 picoseconds, and your high to low transition is around 118 picoseconds, which are all below 200 nanoseconds. So system integration and results. So this is the actual circuit. So from clock generator to the RC sense to your comparator, and then finally to your XOR circuit. So from a schematic perspective, this is what was achieved. So the target range of 1 picofarad to 20.5 picofarad was achieved with a sensitivity of around 4 microseconds per picofarad. And then for the power consumption, so you see linear increase in power consumption as the capacitance increases, having a maximum power consumption of around 247 nanometers. And then this is your final layout showing the clock generator, the RC Csen circuit, and the XOR circuit. And what we're seeing here is that for capacitance of, if the sensing capacitance sees 20 picofarads, this is the circuit that you see. So you have the two clocks at the top, so you have around 90+% duty cycle. And then the trigger, so you see a rising edge, the capacitance being charged, and that triggers the comparator to change its value at the target threshold voltage of 890 volts. And then because this is 20 picofarad, what you see in the phase detector output at the bottom, which is the output of your XOR, is close to 79 microseconds of pulse width, signifying the C-sense of 20 picofarad. So from a layout perspective, the range was maintained to 1 picofarad to 21.5 picofarad, and the sensitivity was still around 4 microseconds per picofarad. And then in terms of power consumption, we see a slightly higher power consumption of 255 nanowatts because of the introduction of parasitic capacitances in the actual layout. So in conclusion, this is the work that was done, highlighted in pink, and then the different types of other similar capacitance sensors. And what we're seeing here is in terms of dynamic range, in terms of power consumption, we managed to implement a very low power circuit that operates at low power consumption. But in terms of dynamic range, it's comparable in terms of the range. So this is close to 20 as opposed to the others, and sensitivity of 4 microseconds per picofarad. So in conclusion, so the system was implemented in a 65 nanometer CMOS technology, given the following dimensions. And the capacitance pulse width converter achieved a range of 1 picofarad to 20 picofarad at a frequency of 11 kHz. And this converter consumed the maximum power of 255 nanowatts, which occurs at the maximum detectable capacitance of 20 picofarad. So with that, thank you. I forgot. I'd like to thank the collaborators of the project, the different ERD team, analog devices, Picari, and of course the Lord from UPE, Mrs. Vergara, for this presentation. Thank you very much. Really? So, may tanong ba? Baka may tanong sa school. Meron ba? Kung wala pa kasi. Ako bila pa na. Sige. Baka pwede naman kung yung tanong, ano na lang, forward na sa mga tao after. Sige. Thank you. Meron ba? Wala. Sige. Thank you very much.